What's up, my stat stars? Michael Princhuk here, and in this video I want to help you tackle 5 really good for response questions that cover probability, probability distributions, and random variables. This unit over probability can be very difficult for students to learn and very difficult for teachers to teach. So I want to provide for you 5 really good questions that are going to help prepare you not only for your unit tests in class, but for the AP exam in May as well. Now, these questions cover the big 5 concepts that come out of this unit. There's a question that covers basic probability. There's one that covers a discrete random variable and a probability distribution. One that covers a continuous random variable through the normal distribution. One that covers the binomial distribution, and one that covers the geometric distribution. If you can master these 5 topics, then you're going to do really, really well on them on your unit tests as well as the AP exam. Now, maybe you really are already good at these topics, and then that way these 5 FRQs could be really just a review for you to continue to help you prepare for the AP exam as well as your unit tests in class. Now, if you're looking for the PDF version of these questions, that way you can try to tackle them on your own first and then watch the rest of this video to see how you did, head on over to the Ultimate Review Packet for AP Statistics. Sign up for a free trial where you can gain access to this document. And while you're there, you might see a lot of other documents, including study guides, practice sheets, practice multiple choice, and full-length practice exams. Basically everything you need to help prepare for what you're doing in AP Statistics in your class, as well as prepare for the AP exam in May. All right, let's start taking a look at these questions and exactly how to solve them. That way, when you see similar questions on your unit test, you'll be ready to crush it. So in the first question, we were told a restaurant tracks the number of customers who arrive during each 10-minute interval. Let the random variable x represent the number of customers arriving in a randomly selected 10-minute interval during lunchtime. The probability distribution is shown below. So this is a discrete random variable because we have a set number of options that's listable, 0, 1, 2, 3, or 4 customers. And we have a probability distribution showing the probability of each of those outcomes. Now, the first question says, verify that the probability is a valid probability distribution, right? Make sure this is valid. So there's 2 things we have to check. First, all probabilities have to be between 0 and 1, which all of these are. And the last thing is that in a probability distribution, everything has to add up to 1 because one of these outcomes has to happen. There's no other outcome. We can't have a negative amount of customers and it doesn't have 5 listed because 5 customers obviously doesn't happen. So we just got to make sure that all of these add up to 1, and of course they do. So here's a nice write-up for that. Each probability is between 0 and 1, and the sum of all the probabilities does equal 1. We showed our work there, adding them all together. This verifies that we do have a valid distribution for a probability. All right, the next question says to calculate the mean or the expected value of x and then interpret its meaning in context. So here we're talking about the mean of the random variable, or you can also write the expected value of the random variable. This is basically the average. So if we were to allow this situation to happen, look at a 10-minute window, look at a 10-minute window, look at a 10-minute window over and over and over and over and over again, and each 10-minute window track how many customers came, 0, 1, 2, 3, or 4, and then find the average in the long run, right? After looking at many 10-minute intervals, what is the average number of customers that we would expect to come? That's exactly what this is. So the formula is very simple. We're just simply going to multiply each outcome by its probability and add them all together. And that is how, of course, we get the expected value. So here's my work showing each outcome multiplied by its probability. And I got 2.25. So the interpretation is, on average, there are 2.25 customers in a randomly selected 10-minute lunchtime interval. Or you could also say, in the long run, after examining many 10-minute intervals, the average number of customers that we would expect to come in any 10-minute interval is 2.25. Now, you can also get this number on your calculator if you know how to enter the outputs or the potential values, right? The 0, 1, 2, 3, 4, and then put in their probabilities. You could use list 1 and list 2, and then you could run a 1 variable stats, making sure that you have that frequency list set as list 2, and then you could get this value as well on your calculator. Now, the next question says to calculate the standard deviation. All right, this is a little bit trickier to do by hand. I will show it, but I would highly recommend using your calculator for this. But basically, we have to take each outcome, each individual outcome, subtract the mean that we just calculated, square that, multiply by its probability of that individual outcome, and then we're going to sum all of the, well, that's terrible. And then we're going to sum all of those together and take a square root. So it's pretty complicated formula. Well, that's a bad formula for some. There we go. Pretty ugly formula. It does take a lot of time to do, but here is my work showing all of that. So it's showing, like, for example, 0 is the first outcome minus the mean of 2.25 squared times its probability, and then repeat, repeat, repeat for each outcome, and then take the square root of all of that sum, and I got 1.0897 customers. You could also do that on your calculator if you know how. All right, now let's dive into some good questions. So the restaurant is considering adding an extra employee if the number of customers in a 10-minute window is 4 or more. Use the distribution to determine the probability that the restaurant will need an extra employee. So basically, we need an extra employee if we know or if we feel that there's going to be 4 or more customers. Well, first off, there can't be or more. It's only 4. 4 is the highest. So essentially, the answer to this question is, what's the probability that there are 4 customers in a 10-minute interval? And that is, of course, 15%. So because there is nothing greater than 4, we would just include 4. So in a randomly selected 10-minute interval, there's a 15% chance that the restaurant will need an extra employee because they're getting that 4 customers. Next question says, given that there are at least 2 customers arriving, what is the probability that exactly 3 will arrive? So this is a classic conditional question that for some kids it gets really tricky, but it's actually meant to be really, really simple. So if we just said, hey, what's the probability of exactly 3? It'd be 0.25 and we'd be done. But there's a condition given that it's at least 2. So we're trying to find the probability that the number of customers is exactly 3 given that it is greater than or equal to 2. And that's going to require the conditional probability formula. So here is my work for that. So in the numerator of the conditional formula is both equal to 3 and greater than or equal to 2. Well, the only outcome that is both equal to 3 and greater than or equal to 2 is 3. It's the only outcome that meets both of those things. It obviously is 3, 3 is 3, and 3 is also greater than or equal to 2. So my numerator is going to be 0.25. The denominator is the probability of the condition, x being greater than or equal to 2. That's going to be 0.35, 0.25, or 0.15. Adding all those together, we get 0.75. Divide, and we get 0.333. So if there are 2 or more customers arriving in a 10-minute window, the probability that there is exactly 3 is 33.3%. All right, that's it for question 1. Hopefully it wasn't too bad, but I tried to cover a couple different questions that all deal with a discrete probability distribution. All right, let's dive into this next question. A delivery driver receives tips throughout the day. Let A be the total amount in tips in dollars received during the morning shift, and let B be the total amount of tips received during the afternoon shift. Let A follow a normal distribution, so he gets a mean of $32 in tips, standard deviation of $5.4. That's in the morning. And then the afternoon B also follows a normal distribution with a mean of $45, so he tends to make a little bit more in the afternoon with a standard deviation of $7.80. Assume the 2 shifts are independent of each other, so how much he makes in shifts A has no impact on B, and B has no impact on A. All right, so lots of really good questions we could ask here. So let's start by saying, all right, let's define a new random variable t, the total amount of tips for the entire day. State the mean and the standard deviation. Well, because both A and B follow normal distribution, when we add them together to get the total, we are, of course, going to also follow a normal distribution. So t is simply the combination of adding A plus B. So now we have to find the mean and the standard deviation for this new random variable. All right, the mean is really, really simple. $32 in the morning, $45 is the expected value in the afternoon. Add those together, so he would expect $77 for the entire day. Very simple. Standard deviation, this is what we got to remember, a really important rule. You cannot add standard deviations. You have to add their variance. So I'm going to take the variance for the morning, which is just 5.4 squared, the variance for the afternoon, which is just 7.8 squared, and then add all that variance, take a square root of it all to get back to the standard deviation for the total. So showing my work there, I get a standard deviation for the total of $9 and about 49 cents. I kept an extra decimal there just for accuracy, but 9.487. So the total is going to follow a normal distribution with a mean of 77 and a standard deviation of 9.487. All right, next question says, all right, compute the probability that a driver earns more than $85 tips in a randomly selected day. So now we're talking about a total. It doesn't say morning or afternoon. This is just our total. So we're trying to find the probability that the total is more than $85. All right, so the process here is going to be to calculate the z-score for 85. So we see where it fits on a normal distribution. And then we could use calculator, t-tables, z-tables, to find the actual probability that we are above that z-score. So here's my work for that. So the first thing I'm doing is I'm once again stating that, hey, I'm trying to find the probability that the total is greater than 85, which would be equivalent to a z-score being greater than the z-score for 85. So there's my work showing the z-score. So I took 85, I subtracted the mean, that's the $77 that we already calculated, divided by the 9.487, that's the standard deviation we already calculated, and that gave me a z-score of 0.8433. So if we're thinking about the normal distribution for this total, and right smack dab in the middle is, a z-score of 0, which would be the $77 that we would expect the total to be. Well, 85 is just a little bit. It's not even one standard deviation above. It's about right here, about 0.8433. That's where $85 falls. And we want to find the probability that we are above that. So this is where you're going to grab your calculator, TI-84, Numerics calculator, or you can use an old school z-table or some computer program or whatever. But the area above a z-score of 0.8433 is 0.1995. So the probability that he makes $85 or more, or greater than $85, is about 20%. 0.1995 would round pretty close to 20%. All right, the next question says, explain why it is appropriate to model the total tip amount T using your normal distribution. I actually kind of alluded to this earlier, but because the sum of independent normal random variables is itself exactly normal, since A and B are both given to follow a normal distribution and they're independent, then the total, a combination of A plus B, is also normally distributed with a mean equal to the sum of the values and the variance equal to the sum of the variances. And then, of course, we square root those variances to get to our standard deviation. But because A and B are both independent and follow normal distribution, combining them in any way, adding or subtracting, would also be a normal distribution. All right, final question here. What is the probability that on a randomly selected day, his tip total for the morning shift will be greater than the tip total for the afternoon shift? All right, this typically tends to be one of the hardest types of questions for students on the AP exam, but we're basically trying to find the probability that the morning, that was A, is greater than the afternoon, which was B. Now, the first thing I like to do here is subtract the B over. So we're trying to find the probability that the difference, A minus B, is greater than 0. Now, typically, A is supposed to be less than B. If you go back to the original problem, he does typically make less money in the afternoon, or in the morning, excuse me, than in the afternoon. But, things could vary. Maybe he makes a little bit less in the afternoon, a little bit more in the morning, and he does make more money in the morning, which is the probability that we're trying to find this question. So the idea here is we need to really investigate the difference, A minus B. We need to figure out what the mean of that difference is and what the standard deviation of that difference is, and then we can figure out the probability. So here's my work showing that. And now let me walk you through this one more time. We're trying to find the probability that the morning amount is greater than the afternoon amount, which is the probability that the difference, A minus B, is greater than 0. All right, so first we have to find the mean for the difference. Well, that's easy. We expect 32 in the morning. We expect 45 in the afternoon. That is a negative $13 difference. We expect $13 less for this difference. All right, what about the standard deviation? Well, we got to remember a couple things here. One, we cannot combine standard deviations, but we don't subtract them either. So we're going to take the variance for the morning. We're going to take, which is 5.4 squared. Take the variance for the afternoon, 7.8 squared. And even though we're looking at the difference, it still adds. Variance always builds, whether you're looking at the total or the difference. So we'll get that same standard deviation after we take the square root of 9.487. All right, so now, here's the deal. We have to find the probability that the difference is greater than 0. So what we have to do is figure out where does 0 fall on the normal distribution. And because A and B are both normal, the difference between them also falls in normal distribution. So we expect $13. That's right smack dab in the middle. That's a z-score of 0. Now, we got to figure out where is 0. Obviously, 0 is going to be somewhere on the right-hand side because obviously it's greater than negative 13. But where is it? Well, that's exactly why we got to find the z-score for it. So we're going to take 0. That's the value in question because we're trying to find the probability that A minus B is greater than 0. Subtract the mean, which was negative 13. So be very careful there because we're going to subtract a negative 13, which is going to make a positive 13, and then divide by our standard deviation. So a difference of 0 is 1.370. That's a z-score of 1.370. So here's a z-score of 1, here's a z-score of 2, here's a z-score of 3. 1, 2, 3. So we're looking at about 1.37, somewhere right around here. So anything over here is going to be where A is greater than B. It means we're going to have a positive difference, right? Because I want A to be greater than B. And if A is greater than B, that means that when I subtract A minus B, I get a positive number greater than 0. Anything below that z-score is going to be, well, when it's expected, and that's the afternoon to be greater. And if I do morning minus afternoon, and if afternoon is greater, that's going to produce a negative. So I want to look greater than 0, so that's a z-score that is greater than 1.370. Again, using a calculator, TI-84, NumWorks, you can find the probability that on a normal distribution, you have a z-score greater than 1.370 pretty easily, and it's 0.0853 or about 8.53%. So it's about an 8.53% chance that he's going to get more money in the morning than he does in the afternoon. That's a very tricky question. I know I explained that kind of quick, even though it did take a while, but I really hope you understand the idea. It all starts with understanding, what are they asking me? A greater than B, subtracting the B over to get A minus B being greater than 0. And then I have to go ahead and figure out, all right, what is the mean difference? A minus B, negative 13. What about the standard deviation for the difference? And then get that z-score for 0, because 0 is the cutoff, right? Anything above 0 is positive. And if A minus B is greater than 0, that means A is positive, right? Right? Just think about that for a second. If A is bigger than B, when you do A minus B, you're going to get a positive number. Anything below 0 means that the B must have been bigger, because if the B is bigger, when you do A minus B, you're going to get a negative. So 0 is that really important cutoff when we're looking at the difference between two things. Greater than 0, A is going to be bigger. Less than 0, B is going to be bigger. All right, hopefully that made sense, because that's definitely a tough question. The third problem is more of a basic probability question dealing with conditional probabilities. So at a concert, security officers check bags for prohibited items. 60% of concert goers bring a bag. Of those who bring a bag, 12% are flagged for additional screening. Of those who do not bring a bag, 4% are flagged for additional screening. So it's really important to understand that this 12% and this 4% are conditional, because the 12% cannot happen until you have a bag, which 60% of people do. This 4% cannot happen unless you do not have a bag, which would be the 40%. If 60% have a bag, 40% don't. So we're going to let F be the random variable where you're flagged for conditional screening, and B be the variable brings a bag. All right, the first question here says to draw a complete probability diagram to represent this scenario. This should be pretty easy. First, you have to be a person going to the concert. Then you either have a bag, which is 60%, or you do not have a bag, which is 40%. Then, as we said, if you have a bag, there's a 12% chance you get flagged for additional screening, which would mean there's an 88% chance you do not get flagged for additional screening. Then the other piece of information they were told us was that if you do not have a bag, there's a 4% chance that you get flagged for additional screening, which would tell us there's a 96% chance you do not get flagged for additional screening. All right, after this, the first question says, compute the probability that a randomly selected concert goer is flagged for additional screening. So we go back and take a look. We see that there are two branches that lead to you being flagged for additional security. You either have a bag and then get flagged, or you do not have a bag and get flagged. So we're going to need the general multiplication rule to figure out these probabilities, because the 12% cannot happen unless the 60% happens first. So that'd be 0.60, you have a bag, and then, because you have that bag, 12% chance you get flagged for additional security. Or, so another branch we're going to add to that would be you do not have a bag, 40%, and then you get flagged for additional security, which would be 0.04. So again, that 0.04 cannot happen unless you don't have a bag. So here's my math for that. So 60% chance you have a bag and then get flagged, 12%, or 40% chance you do not have a bag and then get flagged, 0.04 or 4%. So multiply and add those together, we get a grand total of 0.088. So the probability that any person walking into the concert gets flagged for additional security is about 8.8%. All right, the next question says, given that a concert goer was flagged, compute the probability that the person brought a bag. Okay, if it just said, what's the probability they brought a bag? That'd be super easy, 60%. But there was a condition here. The condition was given that they were flagged. So we're trying to find the probability that the person brought a bag. And like I said, if we stopped right there, it'd be 60%. But on the condition that they were flagged for additional security. So we do have to walk through the conditional formula. The conditional formula on top is going to have both bag and flagged, and the denominator is going to be the probability that you get flagged. So here is the work for that. So as you can see on top is that very specific branch. You have a bag and you got flagged. Again, a lot of kids will just want to put 0.12 there because they read in the problem, 12% chance you get flagged if you have a bag. But what you have to understand is that 12% condition cannot happen unless the 60% happens first. So we have to have 0.6 times 0.12. Now the denominator is what we figured out in the previous problem. The probability you get flagged is 0.088. So multiply the numerator and then divide the numerator by the denominator and we get 0.8182. So if you are flagged, there's an 81% chance, roughly 81% chance that you had a bag, which might have caused you to get flagged. All right. Are the events flagged and brings a bag independent? Justify with appropriate probabilities. Now, it's important that you understand there's multiple ways I can answer this question. Basically, I have two events, getting flagged for additional security and bringing a bag. So to prove I'm independent, I can do one of two things. I could show that the probability of getting flagged, given that you have a bag, is equal to the probability of being flagged. If that's true, then we will have independence. Because if carrying a bag doesn't change the chance of me getting flagged, well, then I guess they're independent. Or I could completely flip those around, right? So there's another way we could do this. We could do the probability of carrying a bag given that you got flagged, and checking that or comparing that to the probability of carrying a bag. Either one of these will work, but you have to be careful. How you do it will change the numbers, and it will also change how you describe it. So I went ahead and I did the probability you are flagged given that you have a bag. This is just how it logically makes sense to me. So on the right-hand side, we have the probability that you get flagged, which we already calculated. So I thought, heck, why not, right? We already calculated that to be 0.088. But we were also told in the very beginning that if you have a bag, the probability you get flagged is 12%. Okay, so obviously if you have a bag, you are slightly more likely to be flagged, 12% versus 0.088. We could also even bring in, we don't have to, but we could even bring in the fact that if you do not have a bag, there's only a 4% chance you get flagged. So if you have a bag, you're more likely to get flagged. If you don't have a bag, you're less likely to get flagged. And I can compare both of those 12%, 4% to the 8.8% chance that you get flagged in general. So these two variables are not independent. And then again, here's how we have to say this. If you have a bag, which is the condition I'm starting with, you always want to start with that condition. If you have a bag, you are more likely, 12%, to get flagged for additional screening compared to the probability that anyone else gets flagged, which is about 8.8%. So hopefully that makes sense. And answering those independent questions is a big task on the AP exam. So hopefully that one makes sense. All right, let's move into the fourth question, which is going to be a binomial problem. So a basketball player makes 78% of her free throws during practice. One day she attempts 12 free throws. Let X be the number of free throws she makes during a randomly selected practice session. So she's going to shoot 12 free throws at her practice. Now, if she shoots 12 free throws, listen, here's what can happen. She can make 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. Those are the possibilities. That's it. All right, first question is, explain why X, the number of free throws she makes out of 12, does follow a binomial distribution. Now, the key thing I always remember here is bi. What does binomial mean? It means 2, right? So we have to be given two things. The probability of successfully making a free throw, 78%, and we have to be given a set number of trials that we're trying to figure out how many makes she could get, which was 12 in this case. Now, a couple other things that are important to check out here. Again, I already said the first one. There's got to be a fixed number of trials. In this case, there's 12. Each trial can only have two outcomes, success or fail. So in this case, she either makes it or the misses. That's another really important part of the binomial distribution is that at any one trial, there's only two outcomes. Third is that the probability of success must stay the same. So it's 78% chance. It cannot change. Now, I wrote assumption there because, sometimes when you play basketball, you start missing a lot and it gets in your head and all of a sudden you start missing more because it's in your head. That cannot happen here. We have to assume that this person will not get a hot streak or a cold streak. No such thing. 78% chance it goes in every single shot, no matter what. We also have to make sure that trials are independent of each other, which is a reasonable assumption for somebody shooting free throws in this context, right? But again, you can easily argue, well, if she starts making a whole lot, she gets a hot streak. We got to assume that this is all not what's going on. And it's simply, hey, every shot is independent of the next. If she makes or misses, it's not going to influence the next. And that probability of success stays the same. So because that, we do have a binomial distribution for our random variable X. where we have 12 trials and a 78% chance of success. All right, so our first question here is, what is the probability she makes exactly 12? So to answer this, we are going to need the formula. Let me just kind of briefly go over the formula here. So the probability in a binomial distribution of any particular outcome is going to be n choose x. That's going to tell us how many different combinations there are, because, I mean, she's going to make 10. Which 10 does she make? I don't care. Which 2 does she miss? I don't care. And that's what that first part's going to figure out. But again, if you use your calculator, it's going to usually do that for you, but you do have to understand that part of it. And then we need p raised to the x, because we need, that many x, a number of makes. And then 1 minus p, that'd be the probability she does not make, and we would need n minus x of those. So if there's x successes, then the remaining must be failures. So here's me using that exact formula to find the actual probability of exactly 10. So we need 12 choose 10. Technically, this line is not there. It's just 12 over 10 there. And again, your calculator is going to calculate that for you. Hopefully, your teacher did talk about it. And then we have 0.78 to the 10th, because we need 10 makes. 0.22, that would be the probability she misses a shot, to the second. Again, if there's 10 makes, there's got to be 2 misses. Now, this first part is simply calculating how many different possible ways there are to do that. All right, you could use a calculator to do this. It's much easier to use a calculator to calculate this, but we do get 26.6%. But you got to make sure on an FRQ you do show the work, and they want you to show that work showing that formula. All right, next question. What is the probability she makes at least 9? So we have to be very smart English students for a second and know what at least 9 means. At least 9 means 9 or more. So that'd be 9 or 10 or 11 or 12. All right, that's not terrible, but I do have to show my work on FRQ, so keep that in mind. So I have to show the work for the probability of 9, 10, 11, and 12, and adding all those probabilities together. And I apologize, these lines should not be there. There's like a little glitch in the system. It should just be 12 over n, right? It should look like this, 12 and then a 9. And again, that's simply telling you how many different combinations there are. All right, so the probability of 9 is about 25%. The probability of 10 is about 26.6%, which we already calculated earlier. The probability of 11 is 17.2%, and the probability she makes all 12 is 5.07%. Adding all of those together, we get a grand total of about 73.9% chance that she makes at least 9 of her shots. All right. Next question. The player claims that she can make at least 9 free throws in 70% of her practice sessions. Based on your answer to part C, is this claim justified? Well, I would say yes. Based on the model that we calculated, there's a 78% chance of success on any one shot. The claim does seem to have support. We predict 73.9% of sessions will have at least 9 makes. All right, that was the probability of 9 or more makes that we calculated. So she's saying that she could do that in 70% of her practice sessions. So I believe her claim to be justified for the pure fact that 73.9 is definitely greater than 70%. So I think she could do it. All right, final question here is going to be a geometric question, and here it is. A company's customer service center estimates that a representative successfully resolves a customer's issue on any given call with a probability of 64%. So call comes into a customer call center. There's a 64% probability that that call gets resolved. Now, we also are told that that is independent of all other calls. So if one call gets resolved, it doesn't impact the next to being resolved or, well, not being resolved. So we're going to let Y be the number of calls until the first successful resolution. Now, that's what makes this geometric. We're looking for the first successful resolution. After that, well, we really don't care. All we care about is the probability of getting Y. How many calls until that first successful call? All right. So the first question says, explain why this is a geometric distribution. So it's a little bit similar to binomial, but binomial, we are given a set number of trials. We're not told that here for geometric. So first, we have repeated independent trials. Every trial must be independent of the next. Each trial can once again only have 2 outcomes. Either we get it resolved or we don't. Success, fail. The probability of success must stay the same. So that 64% must stay the same for every single call. And we're counting the number of trials until the first success. That's that key that makes it geometric. We're looking for that first success. All right, so first question is, compute the probability that Y equals 3. So we're trying to find the probability that the third call is her first success. Now, if the third call is her first success, that means the first call must have been a big fail. The second call must have been a big fail. And the third call, well, that must have been the first success. S for success. And sorry if I missed the handwriting there. So the calculating of this is rather simple, right? So all we have to have is a fail, 0.36 on the first call, another fail, 0.36 on the second call, and then there's that third call that does give us that success. Where'd the 36% come from? Well, there's a 64% chance that she resolves the call. We instantly know the complement is a 36% chance she does not. Now, this is where order does matter. It has to go in this order. Fail, fail, succeed, and that is where I get 8.29% from. All right, the next question says, compute the expected value of y, interpret the meaning of the expected number. So the expected number is the mean of y, or again, we could call it the expected value for y. And in a geometric distribution, very simple formula, 1 over the probability of success. So here it is. If I take 1 divided by the probability of success, which is 0.64, we get 1.563. This means on average, it'll take about 1.56 calls to resolve a customer's issue. Typically 1 to 2 calls, right? 1.56 and 1.2. So basically, if we were to, if this particular person were to keep a journal, and every single time she got a call, she kept track of how many calls she had to get until her first call. And then new trial starts. How many times do I have to go until I get my first success? And then repeat, repeat, repeat. On average, it would take 1.563 calls until her first resolved call. And that actually makes a lot of sense. I mean, 64% chance of resolving a call is pretty high. It should happen on the first or second trial. Now, it could take longer, but the average in the long run is going to be 1.563. All right, what is the probability the first successfully resolved sorry for that typo there. What is the probability that the first successfully resolved call is after the fifth caller? This is a very common AP question because it really makes you think. We want the first success to happen after the fifth caller. So it could be the 6th, the 7th, the 8th, or the 9th, or the 10th, or the 11th. It sounds like it could go anything towards infinity, which seems like it would be really hard. But here's the simple thing. If I want the first success to be after the fifth caller, all that tells me is that the first 5 calls must be failures. And you might say, well, when does the success come? I don't care. It could come on the 6th or the 7th or the 8th or the 9th. But you know what all of those have in common is the first 5 must be failures. So to answer this question, it's actually really, really simple. All you got to do is have 5 straight failures. And then the success can come anytime after that. And I don't care when it comes, but the first 5 must be failures. That will guarantee me that the first success is after the fifth trial. So 0.36 to the fifth is going to be your answer. And it's very, very unlikely because she should get it done in like 1 or 2 calls. So for it to happen after the fifth is going to be very unlikely at about 0.6%. All right, next question. The company is considering offering a bonus to representatives who resolve a customer's issue in 1 or 2 calls. Compute the probability that a randomly selected customer receives a resolution within 2 calls. So again, within 2 calls either means it happens on the first call or the second call. So let's find the probability of Y being 1 or 2. All right, the probability that it happens on the first call, well, that's simple, 0.64. First call gets resolved, done. What about the probability that happens on the second call? Well, that means the first must be a fail, and then the second is a success. Got to be in that order, fail, then success. So add those 2 probabilities together, we get a total of 87.04. So there's an 87% chance that we get that resolution to a call within the first or second call. And again, that makes a lot of sense if you think back about the mean. The mean was 1.563. So in the long run, we should get that first success somewhere in between the first and second trial, right? So it should happen very, very commonly quickly. So hopefully that makes sense. Again, we're just taking the probability that happens on the first call plus the probability that happens on the second call. Calculate those probabilities, add them together, you got your answer. Now, using your answer from Part D, discuss whether offering the bonus to representatives is likely to be frequent, occasional, or rare. Justify using probabilities. Well, we just found out that the probability that you get this bonus, and remember, how do you get this bonus? If you resolve the call in 1 or 2 calls. If you do it within 2 calls, you get the bonus. This is going to happen 87% of the time, so I hate to say it. Based on that probability, achieving this bonus should be rather frequent. It's certainly not going to be rare. Occasional means like every now and then, like 87% chance. To me, that's very frequent. So we would expect many times for the person to get the bonus because they should resolve it within 1 or 2 calls. All right, pretty easy. Hopefully all these questions made sense. Again, a nice little review that really kind of covered all the different big ideas in probability, random variables, and probability distributions. And hopefully you can use these problems as practice to just support what you already know or help you with some things that you might not. All right, best of luck.